Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. So we are going to continue with our next topic, and in this video we are going to discuss on the bipolar junction transistor, or also known as BJT. So beside diodes, which we have covered in our previous videos, the most popular semiconductor devices in the world is transistors. And one of the example of transistors is a bipolar junction transistor and field effect transistor, BJT and FET. In this video, we are going to discuss more details on BJT. Okay, and basically a transistor is a more complex semiconductor, and it can be used in many ways. And let's say, for example, in your hand right now you should have your phone, where in your phone you should have the motherboard, and inside the motherboard the brain of the phone itself, the processor. Okay, it could be any brand, maybe the latest one is Snapdragon, maybe for iPhone is cell A10 or A9. So inside this processor, or this CPU, okay, central processing unit, there will be thousands of transistors inside it. Okay, so the most important features of a transistor is that it can amplify signal and also acts as a switch. Okay, to put it simply, okay, amplification consists of magnifying a signal by transferring energy to it from an external source. Okay, jadi kita besarkan input, okay, menggunakan satu input yang daripada external, okay, menghasilkan satu energi yang lebih besar, yang mana kita panggil benda ni sebagai gain. And then as a switch is when the device is used for controlling a relatively large current between or voltage across two terminals by means of a small current or voltage applied at a third terminal. So untuk transistor kita ada 3 terminal, okay, di mana 2 terminal itu akan menjadi litar yang utama, dan litar ini akan dikawal oleh terminal yang ketiga dengan mengawal, okay, jumlah arus ataupun voltan yang melalui terminal yang ketiga ini. Okay, jadi ia berfungsi sebagai switch. So these two features is very essential in electronics. So using these two features, especially the switch features, okay, it enables us to revolutionize the world of the digital electronics and also the digital memory. So later on in the next video, we are going to discuss on a logic circuit. So transistors is one of the elemental component that helps logic circuit to be possible. So amplification can make weak signal strong, and we call this as a gain. So these are some of the example of transistors that we have. Okay, basically we have 3 different terminals. Here we are going to learn what is the name of the terminal later. So this is also example of modern transistors, and as you can see it closely, one of the transistors is made in Malaysia, and we should be proud because one of the main manufacturer of semiconductors in the world is the companies from Malaysia. So we have a lot of companies that produce semiconductor. Okay, maybe if I can say one is Infineon, ST, and others. Okay, there's a lot of factories and companies in Penang, Selangor, and Johor. Okay, so let's take a look at the transistor structure itself. So we are going to focus on BJT. Okay, the FET will be not covered in this video. So BJT is called bipolar because both holes, the positive, and the electrons, the negative part. So if you still remember in our previous video, we learned about diode, where we have the holes and electrons. okay, where the holes is the P type and the electron is the N type. And we learned that the flow of the electrons, okay, from the N type to the P types to the holes in the P type, okay, will enable the current flow inside the circuit. Okay, so bipolar is basically BJT is basically we can imagine as two PN NP diodes that is being sandwiched together. Okay, let's be sandwiched together, and both holes and electrons are going to take part in the current flow through the device. So we have the N-type region that has the free electron, okay, extra electron, and the P-type regions that contains free holes, okay, or the positive carriers. So there will be two types of BJT. Okay, basically this is the only possible combination of P and N type region. The first one is NPN transistor and the second one is PNP transistor. So the region of the transistor, okay, based from the three different regions inside the transistor itself, can be categorized, okay, and it is named as the first one is the emitter or E, where the emitter function is to send the carrier into the base region and then on to the collector. So the carrier could be the negative carrier or the positive carrier. Uh, so you can imagine that the carrier could be in form of electrons or in form of holes. Okay, uh, based on the type of the BJT, NPN or PNP. And then we have the base region B, where it acts as a control region. It can allow none, some, or many carriers to flow. Okay, so this is the region where we are going to control the circuit itself. And then we have the collector region C, where it collects the carrier, okay, the electrons or the holes. So here is the bipolar junction transistor of PNP. So we have the base, collector, and emitter. So for PNP, the base is negative carrier. Okay, and then we have the circuit of the symbol. Okay, carefully take a look at the terminals C, B, and E. The collector, base, and emitter, and we can also represent with a circle, where basically we are going to focus on the direction of the arrow. So if the direction of the arrow is inside toward inside the base, so it is a PNP. And then we also have the NPN transistor. The difference is just the base is the positive region P type, and the circuit symbols is a bit different, where the arrow is pointing outward, okay, from B to A. So PNP and NPN transistor structure. So basically we are going to have the current flow inside the PNP transistor is from the emitter, okay, uh, into the transistor, and then from the transistor IB, they are going to flow outward, and IC also are going to flow outward. So we can have we can complete the equation that we have learned in the kickoff current law, okay, where IE is equal to IB plus IC. And similarly for transistor NPN, okay, the direction is opposite, where IC and IB is pointing inward towards the transistor and IE is flowing outward from the transistor. So similarly, still the current law KCL is satisfied, where IC plus IB is equal to IE. If you look at the unit here, you are going to see that the unit for IB is in microampere. Okay, and as we have discussed previously, IB is the base the current that flow through the base, where the base are going to be the terminals where it's going to allow some or none or many carriers, either holes or the electron, to flow between between the collector terminal and the emitter terminal. Jadi terlihat current arus IB ni adalah sangat kecil, yang mana dengan arus yang kecil saja sudah mencukupi untuk IB untuk transistor ini berperanan sebagai Swiss, yang akan membenarkan carrier sama ada elektron ataupun lubang untuk melalui antara emitter dan collector. And then we have the transistor configuration. So basically, a transistor configuration is a connection of transistor to get variety of operation. Different kind of purpose will have different kind of configuration. And we see we have three types of configuration: the common collector, common base, and common emitter. If you look here, the circuit is a bit different. For common base, we are going to have the base is set as common, where the input is from the emitter and we have the output at the collector. And then we have the common emitter. The emitter is the common terminal, where the input are from the base and the output is at the collector. And then we have the common collector, where the input is from the base and the output is from the emitter. So let's take a look at the first configuration, the common collector configuration. So the input signal is applied to the base. The input signal is applied to the base, and the output is taken from the emitter, and the collector is going to be the common to the input and output. So basically, we are going to have input is from the base to collector, and the output is from the emitter to collector. So we are going to refer to the collector to calculate the value of the current and the value of the voltage from the input and the output from the base and the emitter. So basically what we are going to have is that the input is equal to the output, in this specific configuration. And then we have the common base configuration. So this is where the base terminal is common point for the input at the emitter and the output at the collector. And this kind of configuration is not really applicable as an amplifier, because the relation between the input current gain, IE, and the output current gain, IC, is approximately 1. So we are not going to have any significant gain or difference between the current from the input and the current for the output. So we can still just use as a switch, but not as amplifier. And then we have the last configuration, which is the common emitter. So emitter terminal is common for the input and output circuit. So we have the emitter as the common terminal, where the input are going to be from the base to the emitter, and the output are going to be from the collector to the emitter. So this is the kind of current flow that we have been introduced in the beginning of the video. And this is basically the mostly applied configurations that act as amplifier in a circuit, because it's going to provide good voltage, current, and power gain. So in this kind of configuration, we can just use a very small, relatively small current for IB for the base, but we are going to get amplified output at the emitter. So let's take a look how a transistor is actually working, when we connect to a circuit. So let's take a look at the NPN transistor structure first. So let's say we have the transistor NPN. We know that This is the emitter, where the emitter is going to be heavily doped. So please remember, in the previous video we have discussed what is the doping process. Just for quick revision, doping process is when we add different kind of elements inside the semiconductor in order to change the number or the amount of electrons inside that area. So if we dope an element with extra electrons, so the materials or the elements, the semiconductor itself, are going to be having extra electrons, and therefore it will be a carrier for electrons, okay, and or also called as the n type. Okay, but if we dope with element with less electrons, or in other words with holes, then it will be a p-type elements. And then we have the base, okay, where the base is thin and it is lightly doped. Okay, there will be a lot of holes, for hole carrier, positive carrier. And then we have the collector, also lightly doped with a negative carrier n type. So we have n, p, n. So if we connect the NPN transistor from the base terminal and the collector terminal B and C with an ammeter, okay, we connect it in series. Okay, we are going to find that connect with ammeter and with the input voltage, we are going to see that the CB junction is reverse bias. Okay, it will be reverse bias. Okay, the terminals here negative, connected to positive. There will be no current flowing in this circuit of C and B. Okay, the collector and the base. So no current flow. And then if we connect input voltage and ammeter to the base and emitter, so we are going to have a forward bias. So remember, in forward bias, the electrons can move through from the N region to the P region, and therefore allowing current to flow. Okay, current to flow. And we are going to have current flowing between E, emitter, and the base, okay, throughout this circuit. So what happens is that when both junction, okay, the B, C, and E is being biased together, okay, we are going to find that, okay, the electrons, okay, that is being forward biased, okay, in the first part from the emitter to the base, okay, are going to flow in this circuit, but in the same time it will also pass through the next region, the collector region, and therefore allowing this circuit to be also forward bias. Okay, so we have forward bias from EB, and then from BC are going to be also forward bias, and therefore we are going to have electrons flowing throughout the circuit. And we are going to note that the current in IB is relatively smaller than the current at collector and the current at the emitter. So this is how we understand that the base, okay, or the transistor itself act as a switch, okay, where we only need a certain value of current to allow the current to flow from E to C. Okay, but when the switch is closed, okay, the current can flow, but when the switch is open, okay, the electrons will not move from E to B, and therefore we can say that the current IB is controlling, the smaller current IB is controlling the larger current IE and IC. Okay. So the current gain from base to the collector is called as beta. So let's say we have IC 99 milliamp, IB 1 milliamp, and IE 100 milliamp. So we are going to get the beta is the ratio of IC over IB, and therefore it will be 99 milliamp over 1 milliamp equal to 99. So the gain that we are going to have inside this transistor is 99. And from kickoff current law, KCL, we know that IE emitter is equal to IB plus IC, and we can prove this by inserting the value 1 milliamp plus 99 milliamp, and we should get that the value of IE is 100 milliamp, so it will satisfy the KCL. So in a PNP transistor, okay, what we have is the hole as the carrier, okay, not the electrons. So we can imagine that the one that move in PNP transistor is the holes, okay, the holes. Obviously, if you want to imagine the electrons to flow, it is also possible. Okay, but we are going to assume that the holes is moving. The hole itself is moving. So what we are going to have is the holes from E, okay, are going to move to B, and then it will complete the circuit, and it will also pass through this border region of B and C, and flow to the collector and complete this circuit. So basically the calculation for the gain will be still the same, okay, 99 over 1 milliamp, and we are still going to get the same result where the smaller current IB is controlling the larger current IC and IE. Okay, but the one that's different is the input voltage, okay, and the structure of the PNP transistor itself. So let's take a look at the schematic symbol. So this is an easy way to remember. You can have your own idea how to remember the direction of the current, the direction of the symbol, the arrow. So for NPN, we can use not pointing in, okay, as to understand or to remember the symbol of the NPN transistor. So if you remember the NPN, so basically PNP would be pointing in. So the BJT itself, the transistor itself, have three terminal. Okay, you are going to find that the transistor will have one flat surface at the body. So looking straight to the transistor up front, okay, we are going to define the right terminal as the collector. Okay, the center terminal is the base, and the left is collector, center is the base, and the right terminal is the emitter. So PNP would be opposite, okay, pointing inward. Okay, the terminals is still the same, CBE. Okay, so let's take a look at the relationship of the current and voltage inside a BJT. So let's first look at the NPN. Okay, so NPN, we have the arrow is pointing upward. Okay, and from here we can also draw the current flow pointing upward. So IE are going to point outward, IB and IC are going to be pointing inward. Okay, IB, IC masuk, IE keluar, macam arah anak panah simbol. So we can define the current IB, IC and IE, and then we can also define the voltage across the terminals. So we are going to have VBC. So VBC is the potential difference between terminal base and the terminal collector, B and C. And then we have voltage VBE. okay, the voltage between B and E. We also have VCE, the voltage between C and E. Okay. So we put uh, the letter at the front as the positive uh, positive terminals. Okay. So C positif, so C kat depan lah VCE. B positif, B kat depan. Okay, kalau kita tukar VEB, so positif will be dekat sini tambah. So let's take a look at KCL. Okay, from KCL we know that IE is equal to IB plus IC. Okay, IB plus IC. So this is for the transistor itself. Okay, not the whole circuit. And then we can also find as in KVL. Okay, so IE is assuming a node, and KVL we assume as a loop. So if we assume that this transistor is one complete loop, we should get that VCE, okay, VCE here is equal to negative VBC plus VBE. Okay, let's say that this is one loop. So negative VBC plus VBE. So we are going to get VCE. So similarly for PNP BJT, okay, this time the current flow would be in opposite direction, i.e. pointing inward. IB and IC will be flowing out from the transistor. And this time we are going to have the terminals will be a bit different. We have VEB, the positive is at the emitter. We have VEC, the positive at the emitter also to the collector. And then we have VCB from the collector to the base. And we are going to get IE is equal to IB plus IC, okay, the same like NPN. Okay, but for the voltage, we are going to have VEC from E to C is equal to VEB minus VCB. Okay, minus VCB. So basically in this figure we can also understand that VBE is also equal to negative VEB. Okay, VCE is also negative VEC. Okay, so it will be the same. And let's say for PNP, okay, we also have, but the terminal is different. We can say that VCB is also equal to negative VBC. So we can always rewrite this equation in different perspective. VEB minus VCB will be VEB plus VBC. Sama je. Okay, so remember that this is the equation to represent the relationship of the current and voltage inside that BJT. Next, we have the DC beta and DC alpha. Okay, so we are going to use direct current, okay, not alternate current. Okay, so the DC beta and DC alpha. What is beta and alpha? So beta we have discussed, basically is the current gain for a common emitter configuration. So if we have a emitter as the common, okay, we are going to use the equation of beta where IC is equal, beta is equal to IC over IB. And for alpha, it is the current gain for a common base. Okay, so we are going to use the equation for alpha is IC over IE. Okay, so how to easily remember is that if it's beta, then emitter will be the common, so emitter will not be included in the equation. For alpha, base will be the common, so base will not be included in the equation. Okay, but both are going to use collector as the output. okay, as the output. So the relationship between the two parameters is that alpha is equal to beta over beta plus 1 and beta is equal to alpha over 1 minus alpha. So take note that alpha and beta sometimes referred as alpha DC and beta DC because the BJT is being dealt in terms of direct current. So now let's take a look at one example. So let's say we have a circuit, okay, with a BJT and three different input voltage and three different resistor. Let's take a look at the circuit first. So we have the transistor. This is the not pointing in NPN transistor. Okay, and we are going to have 4 volt for VBB for voltage at base VBB, and then we also have the 12 volt voltage at VCC. Then we have load 40 kilo ohm at the base. We have load of 500 ohm at the emitter and 1 kilo ohm at the collector. And then we have a voltmeter being attached in parallel to the base V1, V2 at the emitter and V3 at the collector. And we are given that VB equal to V1 equal to 2 volt. So we have VB here. We know that this is VB at the base. And then we have VE. So this is the nodal voltage at the node B. Okay, why? Because we have learned in previous topic, we can find VB. V1 is equal to VB minus ground. So VB minus 0. So V1 is equal to VB. Is equal to 2 volt. And then VE, kalau tak ingat yang pasal macam mana dapat nodal voltage ni, kita please make revision on the previous video. And then we have VE is equal to V2 equal to 1.3 volt. So we have VE. And then we have VC is equal to 8 volt. Okay, 8 volt. So what can be said about the operating region of the transistor? So first, let's take a look at the voltage between base and emitter. So we are going to subtract VB minus VE. So it was given that VB is 2 volt and VE is 1.3 volt. So we are going to get VBE is 0.7 volt. So the value is showing that VBE is forward bias. And then we need to calculate the current IB at the base, okay, where we can use the Ohm's law, okay, I equal to VR, but we need to find the V by having VBB minus VB over RB, and we should get 4 minus 2 over 40,000. We are going to get 50 microamp. And then the current at the collector would be VCC minus VC over RC. 12 minus 8 over 1000, and we should get 4 milliamp. Okay, so we can find the gain beta is equal to IC over IB. So IC is 4 milliamp and IB is 50 microamp. We should get the gain beta is 80. So when we use the equation of beta, it means that this is a common emitter. And then we can find the voltage between the collector and emitter. Okay, by substituting VC minus V, okay, is equal to 8 minus 1.3, 6.7. Okay, so we get 6.7 volt, and we know that this is the operating region of the transistor. Okay, next we have what we call as the characteristic of the BJT. So in figure 9.8 here, we have a BE junction open collector curve. So we have base and emitter, between the base and emitter. So the base current is in the y-axis and the base emitter voltage is at the x-axis. So we can find that after a certain value of voltage, okay, the currents are going to increase at the base, okay, exponentially. Okay, so we have this region where we have the cutoff, okay. And this characteristic is the one that we have learned in diode, okay, where we have the offset voltage and so on. And this is also the characteristic that enable the transistor to function as a switch. And then we also have figure 9.9. Here we have the collector current and the collector emitter voltage.